I'm presenting our paper, ReSTIR Subsurface Scattering for Real-Time Path Tracing, and I want to start with a quick reminder on what subsurface scattering is and how it is integrated into a path tracer. So subsurface scattering occurs in materials that exhibit noticeable translucency, like human skin, wax, marble, or some fruits. And it is an important visual effect for realistic rendering. And here on the right side, you can see that subsurface scattering creates these smooth shadows and handles color bleeding. Here on the slide there is this marble or wax-like statue, and you can see that subsurface scattering results in a more natural look or a much smoother appearance. So from a path tracing point of view, in surface light transport, light reaches the surface and of course is partially absorbed, but the rest is reflected in the same exact position. And in contrast, when we deal with subsurface scattering, light reaches the surface and is able to enter the surface and is scattered multiple times below the surface, gets attenuated below the surface and is eventually re-emitted. Okay, and then continues traveling to the camera. And of course, we can just use a volumetric path tracer to simulate the actual random walks below the surface. However, this is often infeasible in real-time path tracing. That's why the diffusion approximation is often used. So the transported light is proportional to the emitted light and the transported light below the surface. And now, instead of simulating these actual random walks below the surface and calculating the attenuation over this actual distance, we instead can use the Euclidean distance between the entry and exit point and query a diffusion profile to approximate this attenuation. And here on the left side on this slide, you can see an example of a diffusion profile. Oh. Okay, let me quickly reload this. Great. Yeah, okay. Let's stick with this. So so with increasing distance, less and less wavelengths survive this scattering process. So now that you know how we can evaluate such a subsurface path, let's take a look on how we can sample one. And therefore, we use a method from King and colleagues who generate a point on the surface on this translucent object by using race tracing. So given a visible point on the surface, we first select a channel of this diffusion profile to importance sample a distance. And then this point is projected onto the surface by tracing a ray along some chosen projection axis. And of course, multiple intersections can be found in this radius of influence of the diffusion profile. And in this case, we just select one of the intersections as our next path vertex and continue until we hit a light source. Okay, now since we have to integrate over the surface of the object, or at least in this area of influence of the diffusion profile, we have an additional source of variance for our Monte Carlo estimator compared to the standard surface reflection case. And here, wow, that's working great. So one moment, okay, it's working. So here you can see a video of one sample per pixel path tracer, and the path tracer clearly struggles to find these long subsurface scattering paths from the illuminated regions into the darker regions. This is why we want to introduce ReSTIR subsurface scattering, or ReSTIR SSS for short, where we apply ReSTIR to our specific subsurface scattering case. So this video here shows the improvements by our method compared to the standard path tracer. And you can see there's significantly less noise in this region with visible subsurface scattering. So ReSTIR was introduced by Bitterly and colleagues and has become widely adopted in this domain of real-time path tracing since then. And the idea is that we reuse samples by sharing information about found live paths across pixels and frames. And with this spatial temporary use, cost can then be amortized. So some of you might be wondering why we are proposing yet another specialized version of ReSTIR when there's already something like ReSTIR GI or ReSTIR PT. And the short answer to this is that both these methods focus on sampling and reusing surface light transport paths. And with our completely different sampling scheme in our case, for sampling these subsurface paths, we need some specialized techniques to efficiently reuse these paths, as you will see shortly. Okay, but before that, let's quickly recap the fundamental building blocks of ReSTIR. So ReSTIR starts with generating an initial candidate in each pixel, which is then stored in screen space in a so-called reservoir. And the results of this first pass are then fed into a second pass where we apply temporary use. And there the current frame's pixel position is matched with the previous frame's pixel position, for instance using motion vectors. And there we can then query the path stored in the reservoir of the previous frame and replace the current path if the other one is better. Okay, after that, spatial reuse is performed, and there are a bunch of reservoirs of some randomly selected neighbor pixels are queried, and there we evaluate their contribution in our current pixel by shifting the path from the other pixels domain to the current pixels domain. And when a better sample is found, of course, the reservoir is updated again. And with this spatial reuse, then noise is reduced significantly. This means for our ReSTIR subsurface scattering algorithm, we need two things. So the first one is we need to generate subsurface candidate paths. And this is mainly the same as I've already explained to you in the beginning of the talk with some specifics regarding ReSTIR, and you can find more information about this in the paper. What I want to focus on for the rest of the talk is the ability to shift subsurface scattering paths. So given a path X in a neighboring pixel, which we call the base path, okay, I really need to fix this quickly. Let me quickly restart this. Perfect. It's working now. So, as I was saying, so we have this base path in, for example, a neighboring pixel, which we call the base path, and then we need to construct an offset path in the current pixel. And of course, the first two vertices, so the camera vertex and the vertex on the visible point on this translucent object are of course fixed for a given pixel and time, but the following vertices can be generated by using this base path information. So we've started by implementing two shifts that already exist in the ReSTIR literature. And the first one is the reconnection shift, where we reconnect through the translucent object directly to the base path. In contrast to that, it's also possible that we delay this reconnection to one vertex later. And to generate this intermediate vertex on the translucent object, we can apply random replay. Random replay just copies the random numbers of the base path to achieve a similar sampling behavior. So we get a similar point on the translucent object when sampling. Here you can see the two shifts in action. And as you can see, the reconnection shift is superior in these darker regions with visible subsurface scattering. So it's really efficient in reusing these long scattering paths from the illuminated to the darker regions. And on the other hand, reconnection introduces these strong color correlation artifacts in the illuminated regions, and we can avoid these artifacts or at least reduce them significantly with delayed reconnection that is able to sample similar short scattering paths using random replay. This means we need to combine both of these shifts. Therefore, we developed two advanced shifting strategies, and I want to start with the hybrid shift. So our hybrid shift chooses either X2 or X3 for reconnection, and this means we design a criterion that deterministically decides for a given sample whether we want to apply reconnection or delayed reconnection. And our idea here is that we want to separate these two regions, the shadowed one and the illuminated one, where either one of the two shifts works superiorly. And our criterion now works as following. So we want to reconnect the offset path through the translucent object to the base path if the distance between those two vertices is larger than some threshold. And for example, this can be 2 times the mean free path. This is what we use in our paper. And the motivation behind this is that we then found a long subsurface scattering path that transports light all the way from the illuminated region to this darker region. On the other hand, it's also possible that 2 vertices are close together, but there is a shadow boundary. And such a shadow boundary can occur when there is a corner in the geometry. And to detect such corners, we can just compare the orientation of the 2 normal vectors at these vertices. Okay, this means we apply reconnection if one or both of these criterions are met, and otherwise we just use delayed reconnection. And here you can see a visualization of our hybrid shift. And so this visualization shows which shift is selected for the base path with reconnection in blue and delayed reconnection in yellow. And we can clearly see that we achieve the separation of these 2 regions. As a quick side note, this idea of designing a deterministic criterion to select a shift is of course similar to ReSTIR PT's hybrid shift from Lin and colleagues. So they postpone this reconnection to the base path by successively applying random replay so long until the last vertex of this offset path and the next vertex of the base path are both diffuse, and this just prevents that we reconnect to a glossy surface under some arbitrary angle with nearly no light contribution. So here's a comparison with our hybrid shift now. And as you can see, we successfully combine the 2 shifts. This means we can efficiently reuse these long scattering paths while preventing these strong color correlation artifacts in the illuminated regions. So this is a huge improvement. However, if we zoom in, we can see at the boundary that between these 2 regions that there are some artifacts left, some fireflies occur there. And also in the denoised version of the image, we can see that this boundary isn't, that there are some discontinuities at this boundary. So the reason for this is that there is of course a high chance at this boundary that the criterion just selects the wrong of the 2 shifts. And this is why we want to introduce a second advanced shifting strategy, the so-called sequential shift. So as a reminder, our hybrid shift uses this one spatial reuse path where we try to shift a certain sample with only one deterministically selected shift. So we either apply reconnection or delayed reconnection. But there's no chance that we try to shift the same sample with both shifts. And this is why we introduced this idea of a sequential shift. And there we split this number of neighbors we select in this spatial reuse path and split this into 2 passes, into 2 sequentially chained reuse passes, where the first one uses reconnection for all the samples, and the second one uses delayed reconnection for all samples. And this way, it is possible that we can try to shift the same sample with both shifts. So the best shift can be chosen implicitly. Okay, so far so good. But now I want to give you an example to show you that there's currently an issue with this formulation of a sequential shift. So consider we have this base path that is shifted with reconnection to this offset path in this first spatial reuse path. Okay, then we apply this second spatial reuse path with delayed reconnection. And just consider that our now shifted path Y becomes our new base path. So we shift it with delayed reconnection and generate this offset path Z. And so here is the question, how exactly did we generate this offset path Z? So we use random replay to generate this intermediate vertex Z2. This means we copy the random numbers of our base path Y. But now this is where the problem occurs. So we actually do not know the random numbers of this path Y. These are of course not the same as the ones used for our original base path X. So we never computed any random numbers that could explain how X2 is sampled given Y1. So how do we obtain these missing random numbers? And the natural question to ask here is whether we can just invert the sampling procedure. So given y1 and x2, can we just get these missing random numbers to fix our sequential shift? And unfortunately, it's usually not invertible. And the reason for this is that different techniques can generate the same sample. So what do I mean with this? So for example, think about a BSDF. A BSDF, for instance, can have two lobes, a metallic one and a diffuse one, and those lobes are allowed to overlap. This means with a different set of random numbers, it's in fact possible to generate the same direction or the same sample. And in our case of subsurface scattering, we also choose this combination of a projection axis and a channel of the diffusion profile for importance sampling. So when we choose another combination, it's also possible that we generate the same point on the surface. Luckily, Bitterlier and colleagues found a solution for this problem and originally applied it to metropolis light transport. So their idea is that they define this extended path space where they fix this technique. So once this technique is known, they can make this technique specific inversion. Yes, so how do we obtain this extra dimension or this unknown technique? This is why they introduce probabilistic inversion, and the idea there is that they draw new independent random numbers and sample this technique based on the technique's likelihoods. This means in practice that we just evaluate the technique-specific PDF. And in our paper, we then show that this probabilistic inversion can also be used in ReSTIR subsurface scattering or in ReSTIR in general. And we demonstrate how this importance sampling technique to generate points on the surface can be inverted once the technique, so the combination of a projection axis and a channel of diffusion profile is fixed. This then solves our problem with the sequential shift because we can just obtain these missing random numbers when applying random replay by using this probabilistic inversion. Here you can see a comparison between our hybrid and sequential shift. And let's zoom into that image. Here you can see that we get rid of these fireflies and get this smooth boundary after denoising. Okay, now let's take a look at our overall results. So you already know this video from the beginning. This shows the 1 sample per pixel path tracer and our ReSTIR subsurface scattering also with 1 sample per pixel. And we can clearly see that we effectively find and reuse these long subsurface scattering paths. When we apply the denoiser, you can see on the left side that we have there these flickering artifacts because these darker regions are undersampled. And as you can see on the right side, we get mostly rid of these flickering artifacts. Here is now a comparison between the standard path trace and our technique with the 2 shifting strategies and the denoised version of the images. So when you take a look, for example, in the bottom row, you can see that our technique pretty much matches the reference images. Now let's look at some frame times. So the sequential shift is slower than the hybrid shift. Both, of course, as I already mentioned, use the same number of neighbors in total for spatial use, but the sequential shift strategy just divides this into 2 passes. The actual reason, or one of the reasons why this sequential shifting strategy is slower than the hybrid one, is that we have to launch this additional reuse pass and have to load this pixels reservoir and data again, which of course introduces some overhead. So when comparing these frame times with the standard path tracer, we can see that the standard path tracer is significantly faster. So instead, let's take a look at an equal time comparison with 12 samples per pixel. So here you can see that the path tracer works really well in these illuminated regions where direct illumination dominates and there's nearly no noise left. However, it still struggles to find these long subsurface scattering paths. Lastly, I quickly want to address this thing, why we can take comparatively so many samples with the standard path tracer in equal time. And this is largely due to how memory is accessed with our technique. So during spatial reuse, neighboring pixels are randomly accessed, which means that we have random and unaligned access to the VRAM to load this large reservoir data and pixel information. And we believe that with smarter neighbor selection strategies, or with more compressed reservoir or pixel data, or of course with future GPU generations, where the VRAM throughput isn't the limiting factor anymore, that our technique or ReSTIR in general can become even more helpful compared to the standard path tracer. Okay, in conclusion, our technique ReSTIR subsurface scattering significantly reduces noise by using our introduced hybrid or sequential shifting strategies, and achieves this better quality after denoising due to better sampling. With that said, thank you for your attention.
Great, thank you. Thank you for the talk. We have a few minutes for questions, if anybody has any.
Yep.
You pointed back there.
Yeah. Yeah. Sorry, I can't understand you.
Sorry, great talk.
Yeah, thanks.
It seems like you could use the sequential pass, sequential passes, treating the spatial candidate, you take the second spatial candidate to the second shift, the delay shift, and actually derive that shift from the original candidate that you shifted the first time. So shift the reconnection, finalize the reservoir, store a bit that tells you that you didn't choose, if you didn't choose that shift sample, and if you did choose the reconnection shift, give the data around, sort of bit, and finalize the reservoir, shift it again with the second time shift, the reconnection, and the reservoir, then find out why it was so complex.
Okay, so the question is whether we can just use one spatial reuse pass for the sequential shift and just do or just try to do reconnection and then delayed reconnection afterwards, and do not split it into two passes. And the reason for this, or why we choose to make it like this, is because then with your suggestion you have to use both of these shifts every time for this one sample that you select. But you maybe do not want to do this, so you want to be able to select more randomly selected neighbors that you then can shift, if that answers your question. So I think it's possible that you you can do this, but when you first apply this one spatial reuse pass, you can feed these results into the second spatial reuse pass and make much more or get much more improvement by this chain reaction through ReSTIR. So you forward this information to the second pass, and there you can reuse this.
Okay, let's take one more quick question here. The question is, what are the timings compared to base ReSTIR?
Thank you. We didn't actually measure the concrete timings for ReSTIR, but actually what we do, we just apply ReSTIR to this subsurface scattering case and use some more evolved shift mappings. So you can just say that when you just use reconnection or delayed reconnection, that this is your original ReSTIR. So to answer this question is that when you just use reconnection, it's really fast. in our case, because when we reconnect through the translucent object, our visibility is solely determined by the diffusion profile, and we do not have to shoot another ray. So this is much faster than, for example, ReSTIR, when you or something like ReSTIR GI, where you have to shoot this additional ray for occlusion test to make this thing unbiased. For the delayed reconnection, it's of course slower, because you have to do this projection onto the surface again, and then maybe have to test this occlusion behind the translucent object. So this is of course again expensive. So you can compare this to the standard ReSTIR for surface reflection case.
Great. Let's thank Mirco once again for his talk.